All right, so let's tackle everything you need to know for AP Statistics Unit 1, starting off with the difference between categorical and quantitative data. Quantitative data just deals with numbers, so think quantity, numbers, that's stuff like heights, class size, population size, anything you put a number on. And categorical is stuff that's like names and labels, so think like eye color, hair color, you can't put a number on that. So we're going to branch off here and talk about categorical data, which you want to represent with a two-way table. You've probably seen these before, but basically you have two variables on either side, and it just shows you like the cross or the intersections between certain variables. So as you see here, we have math students. Sure, we have 10 math students, but then we also have the internal and external variables that split up the number of math students. So we have 3 math students who are internal, 7 students are external, in the same case for English. So the important thing you need to understand is a couple vocab terms that the AP might use in your teachers might use on your midterm is marginal relative frequency. That's a percentage of the data in a single row or column compared to the total. And if you look at this little chart here, that's going to look at B over D or C over D. So we have our column total, which is just going to be C over D, and then our row total is B over D. The next thing we're going to look at is joint relative frequency. So that's a percentage of data in a single group compared to total. So group here, that might be a little confusing, is just we're going to look at A, right? So that's just a singular variable or intersection that we're going to look at between a certain variable. So that's A over D. And if we look in our two-way table with actual variables, that's something like math internal. So that'd be 3 over 23. Or maybe we want to look at external English. So that's, we look down English, external, so that's 9 over 23. Okay, so next we're going to talk about conditional relative frequencies. That's percentage of data in a single category when you're given a specific group. So now that we're going to be looking at A over B or A over C. Now that's something like just A, right? And then the total in the group or column is just going to be over A over C or A over B. And in our little two-way table, that's going to look like, let's say we're given that the student is in math. So that'd be 10, so our total would be 10. And then we want to know what percentage of that is internal. Well, we have 3, so that'd be 3 over 10 as an example for that part. Okay, so now let's go on to quantitative data. So for quantitative data, you want to know how to describe it. A big part of AP Stat is just interpreting, because a lot of the calculations are pretty straightforward. You have a reference table, you can use your calculator, all that. But you need to know how to interpret. So for quantitative data, use the acronym CSOCS. The C stands for context, shape, or S stands for shape. So is it symmetrical? Is it skewed? Number of peaks? Is it unimodal, bimodal, all that? Look at the outliers, right? Any variable, any numbers or data points that are super out wide compared to the rest of the data. You have your center, right? So look at your mean or your median. You have spread, right? That's just range, your standard deviation, your IQR. And then here's a little tip when you are describing the data is utilize descriptive language like strongly, roughly, like roughly symmetrical and all that. And also use comparative language to maximize the number of points you can get on the exam. Okay, now let's go on to some basic terms you must know. I mean, you've probably seen these before. Mean, that's just the sum of all the values divided by the number of values, or the average. I mean, that's like the average value. Standard deviation is just a measure of variation. And here's an important part when you're describing it in context, okay? So you want to say like the value / context, it typically varies by standard deviation value from the mean of mean. Okay, that sounds kind of weird, so let's look at the example. The average PrepWorks subscriber's IQ typically varies. So PrepWorks subscriber's IQ is the value / context. Always put it in context. Varies by 5 IQ points. So 5 IQ points varies by 5 IQ points. That's the standard deviation from the mean of 169 IQ points. The median is just the 50th percentile. So that's where if you have data, you organize it from least to greatest and then look at the value in between, right? You probably heard of that. And range is just the value, not the interval, the value of max minus min in your data set. Okay, so the last thing for exploring data in this part is how to make box plots. You need to know the 5-number summary. So the first number in the summary is your minimum. That's just the smallest value you have. Then you have the 25th percentile or Q1. That is just in between your minimum and median, right? It's the exact, it's pretty much like the median of your minimum point and 50th percentile, if that makes sense. And then the next number is your median or 50th percentile. Then is Q3 or your 75th percentile, and then your maximum value. Okay, so the next thing is IQR. IQR is just Q3 minus Q1. And that's important because you also need to be able to describe specific outliers and their characteristics, that being low-end outliers or high-end outliers. So low-end outliers, like the name suggests, is just a super, super low outlier. So that's going to be any value less than Q1 minus 1.5 times the value of QR. And the same thing for high-end outliers. That's a super high outlier. That's any value greater than Q3 plus 1.5 times IQR. So make sure you know those two equations. And here we just have a visual diagram because box plots are cool to draw. All right, so to round off AP Stat Unit 1, we just have a couple more terms and then we'll get into normal distributions. The first is officially defining percentile. We did talk about it, but how I think you should think about it is that it is the percentage of values that are less than or equal to a specific value. And then we also have cumulative relative frequency. So that shows the cumulative percentages from each interval up through all the data. And here we have a visual. So you can see here when we have a data point, that obviously is graphed. But when we don't have any data, that is just a straight plateau. And then when we get data again, oh no, it's bugging. Okay, so if we get data again, then that thing is going to go up because it's pretty much like I would say a running total of the relative frequencies. And relative frequency is just like the chance of something occurring. So that's like the occurrence or frequency over the total. Okay, so now let's talk about z-scores. So z-scores are tying back to the idea of standard deviations. Z-scores are simply the number of standard deviations a value is away from the mean, and this is the official equation for it. It's whatever value you're looking for the z-score for minus the mean over the standard deviation. All right, so now we're going to talk about what happens when you transform data. Okay, so let's say you have a data set. What if you added a certain constant, like you added 5 to every single value, or maybe if you multiplied every value by 20, right? What would happen to the shape, the variability, and also the center? Well, here is a summary of what would happen. So if you added or subtracted all the data values by the same amount, the shape and variability will always stay the same. The center, so that's like your mean or median, will move up or down by that amount. Now, if you multiply or divide, that's a different story. The shape will still stay the same, but now your center and your variability will be multiplied or divided by that amount. All right, so now let's talk about density curves and normal distribution. So a density curve is on or above the horizontal axis, has an area of 1, and just shows probability distribution. Note that a normal distribution is a type of density curve, but no, when you talk about a uniform density curve, it's quite rare. You might see questions on this though, but you can see pretty clearly that it has a total area of 1. But the more common density curve you'll see is the normal distribution. You'll 100% see this, and you've probably seen this before. So you need to know pretty much the standard deviation and the 68, 95, 99.7 rule. So 68% of the values from the mean are within 1 standard deviation of the mean. 95% of the values are within 2 standard deviations of the mean, and 99.7% of the values are within 3 standard deviations of the mean. So to solve normal distribution problems, you're just going to use your calculator. I mean, that is the most simple way. So know your calculator commands, go and study those. So norm PDF, that finds a probability at a specific value. Norm CDF, that shows probability that the normally distributed variable is between a set interval, pretty similar to norm PDF. And then we have inverse normal, which pretty much does the reverse of these calculations. It finds a value that corresponds to a given percentile, or on your calculator, it might be denoted as quote unquote area, okay? All right, so the final thing we're going to talk about is super niche, but I'm still going to include it because it's on the CED. That's a normal probability plot. So what it does is it plots the actual values versus the theoretical z-values. Okay, so these theoretical z-values are the z-values you would get if the actual data points were normally distributed. Okay, so it pretty much just shows you how well the data fits a normal distribution, and that's something you might see like that. So basically, all you need to know is that if it's roughly linear when you plot this, or it might just give you the graph, it's going to be roughly normal distribution. And if it's not linear, it's roughly not a normal distribution. And yeah, that does it for everything you need to know for AP Statistics Unit 1. So let's cover the AP Stats Unit 2 content, everything you need to know. So correlation, how exactly do you describe scatter plots? You're going to be using the acronym CDAW. So put it in context, direction is it positive or negative, state any outliers, the form, is it linear or nonlinear, and then the strength of that form. Okay, is it strongly linear, is it weakly linear, all that mumbo jumbo. Now, tying directly into correlation and describing scatter plots is your R value. Super important. Your R value is your your correlation coefficient, and it can range from -1 to 1. The closer it is to -1 or 1, the stronger linear correlation it has. So something like -1 is a perfect negative linear correlation. A positive one would be like a perfect positive linear correlation. Here's some more examples. -0.97 would be considered a strong linear correlation. 0 would be no correlation, and something like 0.021 would be a weak linear correlation. A couple things that do not impact your correlation coefficient is changing your units, right? So if you, multiplied everything by 100, does not change your R value. Also, if you switch the X and Y axis, that does not change your R value. Now let's talk about how outliers affect your R value. So any outliers that are within the pattern of data will strengthen R. Any outliers outside the pattern of data will weaken R. What is the pattern of data? Well, I drew a nice diagram to represent it. So it's basically like the general trend that your points are facing. So this is like our general trend. So if I had a super outlier, like this star I'm drawing out here, that'd be within the pattern of data and strengthen R. But if we had something down here, right, that's outside the pattern of data, that would weaken R. Also remember, correlation does not equal causation. Super important here. You probably heard it before, so just keep that in the back of your mind. All right, so now let's talk about regression lines. So regression lines are essentially just your best fit line. So if you have a scatter plot with points, you put your best fit line on there, and it helps you estimate values for points that you aren't given, okay? So what this looks like on the equation is y hat. You use y hat instead of y, because it is your predicted value, not your actual y value. So it's y hat equals a plus bx. You've seen that form before. A is your constant, b is your slope. Something you probably haven't seen before is your residual. Okay, so your residual is just the degree of error of regression line prediction. Okay, so let's say my actual value is 5 and the predicted value is 10. Then you get -5 as the -5 units as the residual. So that's a negative residual. And negative residuals, that means you overestimated, right? You overestimated by 5 in that case. A positive residual would mean that you underestimated the actual value. All right, so the important thing with, I would say, regression lines is that, yes, you are going to be calculating and extrapolating some values and all that, but I would say the big part is interpreting the regression line with proper language. This is super important. It's probably what's going to be tested on the AP, maybe on your midterm. All right, so here's an example. I just stole this methodology off my AP stat teacher, so hopefully it's not like copyright infringement. But it basically shows you the one way you could use language to interpret the slope, interpret the y-intercept, interpret the residuals, all that, talking about stuff like explanatory variable, that's just the independent variable, your response variable, your dependent variable, and then using that specific and really correct language. And now let's talk about the least squares regression line. So basically you'll get a big data set and you're going to plug it into your graphing calculator, and then you can use the calculator function to produce the least squares regression line. It's the line that minimizes the sum of the square residuals. You don't need to know what that means, but basically it's like pretty much a best fit line, sort of. So the key things you know about this is that you can also find these values, by the way, with your calculator. The S value is your average distance. The predicted values are away from the LSR. And then your R squared value is the coefficient of determination. That's a percent of your response variables that can be explained with the explanatory variable. And for a optimal least squares regression line, you want as low of an S value as possible and as high of an R squared value as possible. Also, sometimes on the AP, you're going to see, I would say sometimes, you're going to see this, the computer printout. Okay, it's kind of weird, I know, but you might have not done this in class. There's just something to keep note of, is just these like computer printouts. This is a nice graphic. It shows you where the y-intercept, the slope, S value, R squared value, yada, yada, yada. You'll learn these other things like TMP and later units, but basically, yeah, just like memorize these values, where they are and all, just so that if it shows up, you aren't just caught, not knowing what to do. Okay, so let's talk about outliers. Okay, so how do outliers affect your least squares regression line? Any outlier okay, is going to decrease your correlation. Now, here's the thing, right? Outliers are added far away from the mean of y, so that's going to be a horizontal line. That's going to decrease your slope and also increase your y-intercept. And the outliers are added above the mean of x, so this case is a vertical line. Your slope stays the same, your y-intercept decreases, and if it is added below the mean of x of that vertical line, then your slope is going to be the same, and your y-intercept is going to increase in this case instead of decreasing. So the last thing we're going to cover now is residual plot. So it pretty much just plots residual values versus the explanatory or independent variable. If there's a clear pattern, that means a linear function is unlikely to be the best fit for the data. If it's an unclear pattern, that means a linear function is likely to be the best fit for the data. And here is a example of an unclear pattern. You can see it's just like pretty much random dots. So in this case, a linear function would be likely. Something like a clear pattern would be like, I don't know, I'm just going to draw something random. Let's say this was the line. And it goes something like this, right? Like a U-shaped parabola, whatever. That means it would be unlikely for a linear function to be best fit for that data. So that does it for all the content you need to know for AP Stat Unit 2. All right, so today we're going to cover all the content you need to know for AP Statistics Unit 3. Okay, so the first thing we're going to talk about are sampling methods. Okay, so the most common one you're going to see is simple random sample, or SRS. It's a random selected subset of the population, and all members in the sample have an equal chance of being selected. And here's the general process you would typically use when doing a simple random sample. You're going to define the population and label the individuals. So what that actually looks like in practice is you're assigning numbers to people, or you're putting their names on a slip of paper. And then number 2 is you have to randomize, okay? That's why it's called a random sample. So you can do randomization through a random number generator, put people's names in hats, whatever. And number 3 is just select members of the sample for your simple random sample. So the next sampling process we're going to talk about is stratified random sample, where you're going to split the population into groups or strata based on shared traits, okay? These are basically shared traits as in like homogeneous groups, okay? You have groups where they share a certain trait. So let's say I had PrepWorks subscribers, okay? I split you guys into PrepWorks subscribers and PrepWorks not subscribers, okay? And then what you're going to do from there is randomly select samples from each group. So if I had 10 PrepWorks subscribers and 10 PrepWorks not subscribers, I'd randomly select, say, 2 people from each group, where everyone in that group has equal chance of being selected. So here's another example. You divide a school by grade level and then randomly pick students from each grade. Now, the confusing part with stratified random sample is there's a very, very particular close second to it, is a cluster sample. Okay, it sounds very similar. You're splitting the population into groups/clusters and then randomly selecting entire clusters. I made that bold for a reason, okay? I made that capital letters for a reason. Entire clusters to sample. So example of that is splitting a city into neighborhoods and surveying everyone in a few randomly chosen neighborhoods, okay? So here's a diagram to make sure that is depicted nicely. So for a stratified random sample, I split it into red people and blue people, right? And then within the red people, I do a simple random sample. And then within the blue people, I do a simple random sample. But for cluster sampling, what I do is my groups, instead of having homogeneous traits, right? In my stratified random sample is either you were red or you were blue. But in cluster sampling, I want equal heterogeneous, like equal representation essentially, right? So basically I have like, some red people, some blue people, yada, yada, yada. And then when I pick who to survey, I'm picking entire clusters. So I pick a random cluster and then I sample everybody in that cluster, okay? The next sampling technique we're going to talk about is systematic random sample. That's where you select individuals at regular or set intervals and you start at a random point. So for example, if I was like sitting outside of my school or something, and every 5th person that walked in, I would give them a survey, right? That's systematic random sample. All right, so we're going to talk about some bad sampling methods. Convenience sample is where you basically choose people who are like easy to reach, easy to access. Example of that is surveying people at a nearby mall only because it's close to you. And the other bad sampling method, there's tons, but these are the most common, is voluntary response sampling. So you allow people to choose to participate. Let's say you put like an online poll, right? Let's say you have like a TV show or something, and then you're like, hey, you should answer this online poll about, said issue. Well, people who feel strongly about that issue are more likely to respond. You're giving them the choice, right? So that introduces bias, and that's why it's a bad sampling method. Here are a couple more shortcomings Number one is undercoverage. So when some groups are left out or underrepresented in the sample. So for example, if you send a survey only to people with internet access, then people who don't have access to the internet can't give their opinion, and therefore that is undercoverage. Non-response is when your selected individuals don't or can't respond. So for example, if you call somebody and you're like, hey, can you do the survey, yada, 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 and they say no, well, that's non-response bias and shortcoming as well. Next up, we have response bias, when people give false or misleading answers. So this is like the equivalent of lying. Now, sometimes it can just be about lying, right? But it's not like explicitly them trying to lie, but it's just that their answers are prone to some sort of bias. Let's say you had, let's say you were reviewing our YouTube channel, right? But let's say you are a friend of me, right? So like you know me in person. Well, then you're going to be having response bias because you know me in person and yada, 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 okay? I think you get the point. Next up is wording of the question. So if you poorly phrase the question or it's a biased question, it influences the answers. So if I ask you, do you want to subscribe to PrepWorks Education? That might be a good question on its own. But if I say, do you want to subscribe to PrepWorks Education to receive $1 million? There's a little bribe at the end, right? So the wording of the question there is poorly phrased, it's biased, and it influences your answer. Okay, so now let's talk about observational studies and experiments. So observational study is different from an experiment because in an observational study, you only observe and collect the data without influencing the subjects. Okay, so for example, if you just sit in your car and then you watch other people in their car and you see how many people use seatbelts in their car, you can't do anything about them, right? You're just simply sitting there and observing variables of interest. The observational study is the direct opposite of an experiment. Now, why? Well, because in an experiment, you are manipulating variables or applying treatments to observe and measure the effects on the subjects, right? And when you conduct an experiment, you want to follow 4 principles. And when you are answering questions, make sure each of these principles are clear in your explanations for full credit. Comparison. You want to compare 2 or more groups to see the difference in the treatment. Random assignment, just randomly assigning subjects to groups to reduce bias. You can also be randomly assigning treatments. Control, so you have to keep all variables constant. You've probably heard of this before. Replication, make sure you have enough subjects. So don't just do an experiment with 2 people. Do it with a sufficient number, respectable amount. A couple more key vocab terms is factor. So factor is the explanatory variable or independent variable. It's just a term used when there are multiple independent variables. Level is just a specific value or category of the factor. So it could be like sunlight is a factor, but then it could be like low sunlight is like level or high sunlight. Confounding is when another variable affects the results. So like if you don't properly have a control group, then it's hard to determine the true cause of your results or your treatment. Placebo is a fake treatment where participants may react favorably to it. Single blind is when the subjects don't know which group they're in, so the treatment being assigned, but the researchers do. Double blind is when neither the subjects or researchers know who gets what treatment or who's assigned to what group. So we're going to finish off with the randomized block design. So a randomized block design is a specific type of experimental design where subjects are divided into blocks or groups based on specific characteristics. So it's kind of like the stratified random sample. And each block is randomly assigned a treatment. And a block is just a group with experimental units with the same characteristic. So here we have a similar study population. So let's say our study population is PrepWorks viewers viewing this video right now. And so we're going to split them into 2 blocks. Okay, we have block 1 is PrepWorks subscribers because they all have the same characteristic, right? They're all subscribed to the channel. And then we have another group or another block is not subscribers. They have the same characteristic. They're not subscribed to our channel. And then from here to actually conduct the experiment with the randomized block design to properly do it, we need to assign treatments, right? So I don't know what experiment we're running, but to assign the treatments, we need to randomly assign the treatments. And we can do that with, random number generator, names in a hat, whatever. All right, so the last experimental design type we're going to talk about is matched pairs design. Okay, this is a specific type of experimental design where your subjects are paired based on specific characteristics, and each pair is randomly assigned a treatment, or one subject in each pair could be a control. So example of this is think about, let's say you're doing an experiment and then you want to sort of like eliminate bias based on gender. Then you can pair like a male with a female, and then have one of them be the control group or just randomly assign the treatments between them. So yeah, that was a lot of vocab and not a lot of, crunching numbers and stats. I know it's weird. There's a lot of interpretation here. Make sure you really know these vocab terms because that serves as the basis of your interpretation and designing your own experiments and, interpreting, is this a bad sampling method and all that. But yeah, that does it for all the content you need to know for AP Statistics Unit 3. I'm going to cover everything you know for AP Statistics Unit 4, which is going to cover topics on probability and also random variables. Do you see this? There's a lot of content, so let's just get right into it. So what is probability? Well, it's the chance that something happens, and it's written as 0 to 1. So if it's 0, it's impossible. 1 means 100% chance of happening. It's unpredictable in the short term and predictable in the long term because you have to observe many, many trials of the same proportion of the random chance process before it actually starts to approach its actual probability value. So let's say my chance of making a free throw is 50%, right? So if I shot 10 shots, it's likely that I only make 5, but I might make 4, I might make 6. But if I shot 1,000 free throws, it's much more likely because of the many, many more trials that I actually have a proportion equal to 0.5. So for simulation, it is just a model used to mimic real-world events to estimate probabilities. You can use a 4-step process to conduct a simulation. You're going to define the problem with the question. Then you're going to describe how to use a chance process like random numbers to model the situation. And then you're going to actually perform that. And then based on your results, you're going to estimate the probability. Now we're going to talk about probability rules. To talk about probability rules, we first need to get a couple of definitions out of the way. The first one is mutually exclusive, okay? 2 events have no overlap and cannot occur at the same time is the definition for a mutually exclusive occurrence. So you can see here, this is a nice diagram. You have event A and event B, right? They're mutually exclusive because there's no overlap, right? They cannot occur at the same time. But if they're not mutually exclusive, they can occur at the same time. That's why there's the overlap in the Venn diagram. The next one is independence. So 2 events are independent if the outcome of one does not affect the outcome of the other. So for example, if I flip a coin and I roll a die, the result of one does not change the result of other. If I flip a coin, right, whatever I get, head, tails, whatever, me rolling a die, because I flipped a head or because I flipped a tails, that doesn't change what I'm going to get or the probability of what I'm going to get on the die. So probability rules. So let's say I have 2 possible events and their probability of occurring is probability of event A and probability of event B. How would I find the probability of either one occurring? So it doesn't matter if it's probability of A happening or probability of B happening. If these 2 events were not mutually exclusive or if both of these events could happen at the same time, I would add the probabilities and then subtract the overlap. If they were mutually exclusive or they cannot happen at the same time, I would simply add their probabilities. And these equations are on the reference sheet. The top one is not the mutually exclusive one, so just make sure you remember that. So now, what if I wanted to find the probability of both event A and B occurring at the same time? Well, if they were not independent, you would just multiply the probability of A with the probability of B given A. If they were independent, you would just simply multiply them. And these equations are also given on the reference table. But now let's talk about the complement rule. Okay, so that's cool and all, but what is the probability that A does not occur? Well, the probability of A not occurring is just 1 minus the probability of A. That's given as a complement rule on your reference table as well. Actually, I'm not sure if this one's on your reference table, or reference sheet, so make sure you check that one. But we're going to move on to visualizing probability in 3 ways. So there's the Venn diagram, which obviously shows the chance of something happening, event A and event B, and then their overlap. And you have a 2-way table. You've probably seen this back in Unit 1, just displaying the data. And then you also have a probability tree. The thing with this is I do have an example for this, but I would say that visualizing the data is really coming down to just personal interpretation. So if you are a little confused, pause the video here. I do run through an example here as I scroll down that sort of explains how to interpret the data. But if you are comfortable with the 2-way table and the Venn diagrams and understand how we're getting these probabilities, if you're trying to brute force it, it's very difficult and it's very hard to visualize. But I'm telling you, just tie it back to the probability rules, okay? Like my entire explanation over here is just using probability rules and then tying that back into what I see on the Venn diagram, the two-way table, and then if you want an easier visual, look at the probability tree as well. So let's move on to the random variables. So we have 4 types: discrete, continuous, binomial, and geometric. Okay, so your discrete random variable is a random variable that takes on a specific countable values. So think of like the number of heads that you flip in 3, the number of cars sold by a dealer in a day. So it's like quantitative numbers. Now, when you have a continuous random variable, that means it's any value within a range or interval, right? So it's not just 1, 2, 3. You actually count what's in between 1 and 2, right? It's continuous. It's everything in between as well. So think about the height of students in a class, right? So if you think about heights, it's not just, you can be 1 inch or 2 inches. Obviously, that's super short, but you can be everything in between, right? Also, the time it takes to finish a race, right? It's incremental. It's not just finishing a race in 1 second or 2 seconds. It's also, you can be like 1.1111. You get the point, right? And here is another diagram just to show the difference between discrete and continuous variables. All right, so if you want to find the mean and standard deviation of discrete or continuous variables, you can also use one variable statistics on your calculator. And a common calculation you will probably have to show for a discrete random variable is calculating the mean or expected value / weighted average. It is the average value over many repetitions of the same chance process for this discrete random variable. Here's an example. You can see X basically just describes the value of that discrete random variable, and then P of X is just the probability of each of those variables. And so what you would do is quite literally just multiply across 1 times 0.1, 2 times 0.3, all the way to the end. And then whatever you get, you add everything, and that is your mean weighted average expected value. So now obviously we have to talk about, can't be stats without talking about how you transform probability distributions. So here's a summary. If you add or subtract the same constant C to each data set, the shape unchanged, center increases or decreases by C, variability remains unchanged. If you multiply or divide by the same constant C to each value in the data set, your shape stays the same, center multiply or divide by C, and variability multiply or divide by C. All right, so here are a couple more equations you need to know when you are adding or subtracting sets of data for random variables, assuming that event A and X are independent events. So you can see we have the equation for finding the mean and median of X plus Y and X minus Y respectively. So make sure you have these equations down. All right, so now we're going to move on to binomial random variables, and I'm going to tell you this is all you need. Okay, you need to know the acronym BINS. Okay, first off, is it binary? Does it satisfy the binary? There has to be a success and there has to be a failure. Are the trials independent? Is there a fixed number of trials? And is there a set probability of success for each trial? So make sure for questions, you address each part of BINS, B-I-N-S, explicitly and show that the events satisfy the binomial settings to prove that's actually a binomial random variable. For the mean and standard deviation, these are on your reference sheet. We have the mean and the median, not the median. The standard deviation where n equals the number of trials and p equals the probability of success. And I would say you can always abuse the calculator for these problems as well if you're asked about binomial random variables. So here are the calculator commands. You got binomial PDF, that's just NPX. So n is number of trials, p is the probability of success, x is the number of successes, and it calculates the probability of exactly k number of successes in n trials. Honestly, this should be x number of trials. I should change that. Oops. X number of trials. Okay, binomial CDF, NP lower and upper bound. It's like the same thing, except it's the cumulative probability of having k or fewer or more successes in n number of trials. It really depends on the parameters that you put for the lower or upper bound. So yeah. Now we're going to move on to geometric random variables. So these are a type of discrete random variables that models the number of trials required to achieve the first success. It's highlighted, it's bolded, the chance to achieve the first success in a series of independent trials with 2 possible outcomes, success or failure. So very similar to the binomial random variables. So example of this is you're flipping a coin and you're trying to see the number of flips it required to get the first heads. That is the example of a geometric random variable. Here are a couple criteria. The trials have to be independent. Each trial has to have the same probability of success denoted by P, and the random variable counts the number of trials until the first success occurs, like we talked about before in the definition. Now, easy way to tell geometric random variables from binomial random variables is the following. Binomial random variables have fixed number of trials. Geometrics do not have a fixed number of trials, so look out for the keyword until. More calculator abuse and commands, geometric PDF and geometric CDF. So yeah, if there's one thing you learned today is learn how to use calculator commands because it makes your life pretty darn easy. And then for the mean and standard deviation of geometric random variables, we have the mean is just 1 over the probability, chance of success, and then standard deviation is square root 1 minus probability of success over probability of success. So that does it for all the content you need to know for Unit 4, probability and random variables. All right, so today we're going to go through a quick review of Unit 5 of AP Stats, sampling distributions. This one really provides the basis for the rest of the curriculum. So let's get right into it. So first we need to differentiate between a statistic and a parameter. A statistic is just any number that describes something that comes from a sample of data, and then the opposite of that is the parameter, which is anything that describes something that comes from an entire population of data. The most common ones is mean and proportion, which we'll get and dive more into later. But there are other ones, like you can see, there's like slope and stuff. There's a unit on that as well, chi-squared. But what we need to know right now is what exactly is a sampling distribution? Well, it is a probability distribution of a statistic that is obtained through repeated sampling of a specific population, right? So let's say your population, I say it has like a mean of 10, right? So what I'm going to do is I'm going to conduct simulations, right, and take repeated samples from that population, find the mean of those samples, and then each of those means of the sample counts as one data point. And then I'm going to put that data point on a new distribution, and then I'm going to do this simulation multiple times, and then I'm going to ultimately find the mean of this new sampling distribution. And theoretically, it should line up because it is an unbiased estimator, right? Which is when the statistics sampling distribution is equal to that of the parameter, right? Like we said before with the mean, a mean is an example of an unbiased estimator because if we have the mean of the population at 10, if we do the repeated sampling and then take the means of those should also equal 10 in the long run, okay? So now we're going to dive into more specifics. The first is more specifically talking about proportions. So like we said before, here's a simplified basically what we're actually doing. We're going to take repeated samples of the same size from a population, then find the proportion of each sample, and then plot that information on a distribution, okay? So we're going to dive into a couple key components. We're not going to do any full significance tests or confidence intervals in this unit, but this is stuff that you need to know and you need to understand in order to do those in later units, okay? So we have finding the mean and standard deviation, basically a bunch of formulas. These are on your reference sheet. I'm not going to, go too much into this to waste your time. We need to know that increasing the sample size will decrease your variability, right? Because if you're increasing the sample size, it's more accurate, right? So then you get less variability. Now we're going to talk about a couple assumptions and conditions. So basically in order to conduct a significance test, these are a couple things that have to be true. First, you need random sampling and assignment. Then you need to satisfy the 10% condition. It's basically where each sample that you take has to be less than or equal to 10% because you want the trials to be able to be treated as independent, right? Where we don't have like replacements. So that is represented as n is less than 0.1 or 10% of the entire population, which is denoted as big N. Then last one is large counts condition, right? So basically what you need is the number of successes and failures have to be both equal to or above 10, and that is the formula for it. That is basically where you have the number of the size of your sample, n, times the proportion, n times 1 minus p, so that is going to basically represent the number of failures that you have. Now, it's also important to note that if your sampling distribution is approximately normal, which it should be because, remember, we have to satisfy the large counts condition, then we can find the z-value, which is the number of standard deviations away that our, statistic is away from the mean. So in that case, once we get the z-value, what we can do is solve for the probability of something, right? Because a lot of times these questions are going to say like, what is the probability that the sample proportion is blank percent less than or equal to or greater than, right? In that case, we can calculate the z value either using a formula, as you can see here. So put it down so the entire formula shows, or you can just plug it into your entire calculator and it does all the math for you. But to solve for the actual probability, guess what? You're also going to use your calculator using normal CDF, or you can use table A. All right, so now jumping over, very similar. We're going to be talking about means to finish off the unit. You're going to be taking repeated samples just like the proportions, but instead of taking the proportion of each sample, you're taking the means of each sample and applying that onto a distribution. You have some more formulas for the mean and standard deviation of the sampling distribution there. These are also on your reference table. Increasing sample size, same thing here, is going to decrease the variability. And then you also need to meet pretty much the same conditions: the random sampling assignment, 10% condition, a large counts condition. Now, I do want to note that you would do random assignment. That is usually only for experiments, but if you're doing samples, usually it's just random sampling. And then there's the formula for the z-value. Again, you can just use your calculator. Honestly, the most important thing in AP Stat is know how to use your calculator, because that will carry you a lot. If finding the probability is the same thing as finding the probability for proportions. And then another thing we want to introduce here is the central limit theorem. Okay, so your sampling distribution is going to be approximately normal, even if the population distribution isn't, if it meets the central limit theorem. Okay, what is the central limit theorem? Basically, all your sample size just has to be at least 30, right? So that is pretty much the entirety of Unit 5. Here everyone, so today we're going through all the content you need to know for Unit 6 of AP Stat, which is inference for categorical data, more specifically proportions, okay? So the first thing let's touch upon is, what is a point estimate? It's just a value, more specifically a statistic that estimates your population parameter, okay? So let's say I have a confidence interval of 3 to 5, then your point estimate would be right in between that, 4. So it's just a number that estimates it, because you're not going to be exact, but we're going to be using a confidence interval to test to find the actual population parameter. Now, a key thing to know is the difference between a confidence interval and a confidence level. Your confidence interval is the range of values that estimates your population parameter. It's pretty obvious. But your confidence level is that like actual percentage, like 90%, 95%. That's the probability that the parameter falls within a specified range. And something to note here is the actual interpretation, because what you need to do is this first part, that confidence interval interpretation, that is your conclusion. Your conclusion needs to conclude in context. And so you're going to say this: we are blank percent confident that the interval from blank to blank captures the true parameter of interest in context. So you need to have that down for the actual confidence interval. But then a lot of times you're going to see an FRQ a follow-up to that question dealing with confidence level and asking you to interpret that. So just have this in mind as well. And now a couple more caveats before we move on to the actual confidence intervals is that if we increase that confidence level, not interval, that's going to increase our margin of error and make it wider. If we increase the sample size, right, so we're getting more accurate, we've talked about this in sampling distributions as well, it decreases our margin of error, which makes it narrower. And also, this is really important, you're going to see this on a multiple choice, I bet. Bias does not affect margin of error. So this is going to be like one of those answer choices about like what affects margin of error. And one of the answer choices is going to be bias. It does not affect margin of error, okay? So the acronym you need to know is PANIC, which stands for parameter of interest, and then your assumptions and conditions, and the name of the test, state that interval, and then finally just conclude, okay? So for a parameter, you're basically saying like what you're actually doing the interval about, right? So if you have a 1 sample, it's just the true proportion of whatever. And if you have 2 samples, then just state the true proportion of whatever and whatever number 1. So number 1, number 2, right? So it's the same thing, except you're doing it for 2. Name of the procedure, pretty simple. If it's 1 sample, you're just doing the z interval for p. If it's 2 sample, it's p1 minus p2, because you're trying to find that difference to see if there is a difference in proportion. Conditions, these we covered in sampling distributions as well, so make sure you really have those down in sampling distributions. Your random sample, your independence based on that 10% condition, then your large counts, and everything is the same for a 2 sample, except now you have to do random sample and everything for both of them. You have to check for 10% condition for both of them. It's very annoying, but you gotta do the large counts conditions for both of them.
So yeah, that's just something to keep in mind. Now, to calculate the actual interval, you can use your calculator, which is highly recommended, or you can be a weirdo and calculate it with this formula, the point estimate plus or minus that margin of error, which is the z star value times the standard deviation. And finally, conclude, right? That's the last part, just conclude within context. So you can see, again, this interpretation part, this deals back with our confidence interval and how to interpret it. So really have that down and do lots of practice problems to hammer it in. Another note is that if your two-sample confidence interval contains the value of 0 within it, then you cannot conclude a difference in population proportion. The reason I included this is because in follow-up questions, you're gonna have like you're gonna do your test and then get like a value of like -1 to like 3.2, and then in the follow-up it's gonna ask you, can you conclude a difference, or yada yada yada, or something like that. And then it's going to include 0, so then you got to remember that you cannot conclude a difference because it includes 0, right? Because it could just not have a difference, right? Okay, so that is confidence intervals, but now for proportions, you also have significance tests. For significance tests, you're going to use the phantoms acronym. So your parameter of interest, just like the same as confidence intervals, but now you're going to have hypotheses. You're going to have HO, which is your null hypothesis, or it is the stated distribution of the category, whatever. Okay, yeah, that long definition. And you're also going to have your alternate hypothesis. Basically, the stated distribution of the population of interest is not correct. So your null is like what they claim, and then your alternate hypothesis is like what your like alternative is. Like you're trying to prove the alternative is right if there's like significance. Okay, it'll make more sense when I get to the actual test itself. And then you have your assumptions and conditions just like normal. It varies a little bit. The name of the test, significance test, calculate the actual test statistics, or test statistic is more of so a value just to evaluate the actual test in of itself. Now, usually you can just use your calculator. If you use a significance test command, it'll just give you the test statistic yourself. Don't calculate it by hand with formula. That's just, don't do that. And then find your actual p-value. Your p-value is what determines whether you are going to reject your null hypothesis or fail to reject your null hypothesis, okay? So your p-value is super important. Usually you're going to be dealing with the alpha value of like 0.05, right? So if it's like below 0.05, then it's statistically significant and you would reject HO. And then if it's above that, you cannot do that, right? Remember all that? And then you're going to make a decision, right? You're going to reject or fail to reject HO. And then finally, just state your conclusion in context. When you state your conclusion in context, that's very important. That's when you're touching upon HA, right? Your alternative hypothesis. When you make your decision, you don't have to say HO in context, but when you do the latter part for HA, you do have to say that in context, okay? All right, let's get into the actual test itself. A lot of the same things. So for one sample, you're just talking about P, and then your HA. And then for a two sample, you're doing, there's another way to say this. Instead of saying P1 is equal to P2, you can also say P1 minus P2 equals something like 0. Okay, so basically there's not a difference. The name of your procedure, right, it's a one sample Z test for P, or if you're doing a two sample, it's just a two sample Z test for P1 minus P2. Your conditions, random sample, like always, then your 10% condition, and then your large counts condition, right? Very similar to the confidence interval. For two sample, it's the exact same thing, right? Except now you got to make sure it works for both samples. Cool. All right, finally, just make a conclusion. This is very important, actually, so I'll just like make sure you can see this entire thing. Pause the video so you can actually interpret this. This is basically what you need to have in the bank for interpreting, okay? Interpreting is super important, having the right wording, making sure you have the right phrasing as well to get all those points. So there we have it for the one sample and then the two sample. Cool. Now, the final topics in this thing we need to cover are type 1 and type 2 error and then power, okay? So when you're talking about significance tests, usually they won't explicitly make you talk about type 1 and type 2 error or power. These are just like extraneous concepts that come up when follow-up questions about significance tests. So it's just good to know them because they might show up. So type 1 error, I like to think about it as a false negative. So this is where the null hypothesis is true, but we reject it and conclude HA, right? So there's really no way else to explain this. But something else to know is that your alpha value is equivalent to the probability of your type 1 error, okay? So if you increase the alpha value, the probability of making a type 1 error is also going to increase. And then you have the other type of error, which is pretty much the opposite. Instead of a false negative, it is a false positive. That's where your null hypothesis is actually false, but we failed to reject it. And then instead, we cannot conclude HA. Okay? All right. The last thing here is power. Okay, so what exactly is power? Power is the probability that our null hypothesis will be rejected when the alternative is true, right? So the chance of making a right decision when HO is false because HA is true. So the equation for this can also be shown as 1 minus the probability of making a type 2 error. And then how do you increase power? There's three main ways. You can either increase the alpha value, but it also has that drawback of increasing type 1 error. Like we talked about before, you can increase the sample size, or you can increase the distance between your null and your alternative hypothesis value, okay? So if you do that, then the test is going to be more sensitive to large changes, and it's going to detect a significance if there is a difference, right? So if you had two values like 2 and 3 and they're close together, then it's going to be harder to tell versus if you have like 2 and 100 as your null and alternative hypothesis respectively. So that does it for all the content you need to know for Unit 6. All right, so today we're covering all the content you need to know for Unit 7, Inference for Quantitative Data Means for AP Stats. So if you understand Unit 6, which is basically the same thing but for proportions, then you're going to be set for this unit. There's just like two things that change. First, instead of using a critical z-value, instead our critical value is t star, okay? So your t star value you can calculate with your calculator, but to do that, you need to also understand your degrees of freedom, which is a new concept and variable. You're going to be using this in chi-squared stuff as well. So your degrees of freedom is a number of values in your data that can vary freely without affecting the others, okay? So it's a really weird definition. You don't really need to understand what that means. Instead, you need to understand how to calculate it. Very simple here for confidence intervals and significance test of means. This is how you're going to calculate it. Your number of degrees of freedom is n minus 1. So your sample size minus 1 is just your degrees of freedom. That's all you need to know for that part, okay? So now let's dive into the actual confidence interval and then the significance test. So very, 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 very similar procedure to proportions. We're going to define our parameters. So instead of the true proportion of something in context, now it is the true mean of something. And if it's a 2 sample, then you're going to do that for both of the samples. Then you're going to name the procedure. Okay, either it is a 1 sample, notice t interval for the mean, and then a 2 sample t interval. Instead of a z interval, we're doing a t interval, right? Because we're using t star instead. Then your assumptions and conditions. This is where we bring back that stuff from Unit 5, sampling distributions. Remember how we talked about central limit theorem? Well, now we're talking about that again. So obviously we have random sample or assignment or whatever. So that is the same. And then you're going to have that 10% conditions. That's the same. And then our third condition here that we need to satisfy is kind of weird. Okay, I'll explain it. So this, number 1, has to be satisfied. Number 2 has to be satisfied. But number 3 is weird because we have 3 different ways here that's shown that we can show that our distribution is approximately normal. Either our population is literally normal because it's stated, or we can say it's normal by the central limit theorem, where our sample size is greater or equal to or greater than 30, or our data doesn't have any strong skewness or outliers. We can also say it's normal or approximately normal in that case. So it just needs to satisfy one of these 3 conditions to say that it is approximately normal and satisfy that third condition there. And it is the same thing for a 2 sample, except guess what? You're going to do it for both of those samples. Kind of tedious. Okay, so the next part is the interpretation, okay? So when you're interpreting, this is basically like your conclusion. So remember, we're talking about how to interpret confidence intervals. That's different from interpreting confidence levels. So make sure you really have this down. I'm sure if you do this a couple times, you're going to have that interpretation down for confidence intervals. But it is the true mean, the true difference in mean. So make sure you have that down. Okay, cool. Well, this video is going to go pretty quick because significance tests are pretty simple for means. We're going to write our hypotheses and define parameters just like those for proportions, right? So you got your null, and then you got your alternative, and then defining our parameters here, the true mean of whatever, and then same thing for the 2 sample. Name the procedure, so it's a 1 sample t-test for our mean, or a 2 sample t-test for a difference in those means. Next, let's move on to assumptions and conditions. Random sample like before, 10% condition like before, and then the same thing with having to satisfy one of these 3 to show that it's approximately normal. Same thing for 2 sample, gotta do it for both samples. And then the last thing here is our interpretation or conclusion. Again, really have this down, okay? Do lots of practice problems so you really get into the flow. If your p-value is less than 0.05, then, well, assuming your alpha value is 0.05 usually, then it's statistically significant. If it's above that, it's not statistically significant. So make sure you reject or fail to reject HO accordingly, and then conclude or cannot conclude HA. That does it for all the content you need to know for AP Stats Unit 7. Alright, so we're moving on to Unit 8 of AP Stats, which has to do with inference for categorical data chi-squared tests. Okay, so this, if you're going to guess, is very similar to significance tests for proportions and means. I mean, the rest of AP Stats is pretty similar, so if you get one down, you can pretty much get the others down too. But there are some nuances you have to know with chi-squared. But this thing is like only 2 to 5% of your AP exam, so it's not that really that important. You're probably not going to do a full chi-squared test for your FRQs. This is more likely to show up as multiple choice, okay? So the first type of test for chi-squared is a chi-squared test for goodness of fit, okay? The key question I like to ask myself is, does the sample's observed distribution significantly differ from the expected distribution? So that's a mumbo-jumbo, jargon term, but let's think about it in terms of something more simple, like M&Ms, right? So let's say I have whatever company owns M&Ms. They claim that it's like 10% red M&Ms, 13% brown M&Ms, etc., right? So then I order a bunch of M&Ms, and then I, open them up, and then I check the distributions, right? I count them up, right? I'm trying to see if my sample, the percentage of X color of M&Ms, matches with what the company claims, right? So that is an example of where you would use chi-squared test for goodness of fit, okay? Now, something that actually differs between chi-squared tests and the significance test for, say, proportions or means is you actually don't have a parameter of interest, and you also do not have a sample statistic, okay? Instead, we're going to jump straight into the hypotheses, your null and your alternative hypothesis, then your assumptions and conditions, so a random sample, the 10% condition, your large counts, except now, instead of it being above 10, it has to be equal to or above 5. I don't know why that is. I mean, whoever created the AP Stats curriculum or whoever invented statistics, you can ask them. Name of the statistics is chi-squared test for goodness of fit. Your test statistic, I guess something cool you can know about this is that a higher test statistic means a higher discrepancy from the expected distribution, which makes sense, right? Because it is your observed value minus your expected count over your expected count. It's like squared and stuff. So if your observed value, if this value, I should not have drawn that arrow. If this one is very high, right? So that means like I'm expecting a value of like 10, but I get like 1,000, then my difference will be super large. That gets squared. And so a higher test statistic means there's higher discrepancy. And, if I'm talking about in terms of like M&Ms, then the M&Ms people, they're probably not telling the truth, right? There's a huge discrepancy. Now we're talking back to degrees of freedom. So instead of our sample size minus 1, very simple now, it's just the number of categories we have minus 1. So in terms of M&Ms, it's like each color of M&Ms, right? If I have 7 colors of M&Ms, then it'd be 7 minus 1. Degrees of freedom is 6. Then we're going to obtain our p-value. You can use table C, or you can just use your calculator. Pretty simple. Then you're going to make a decision, are you going to reject or fail to reject HO? And then you're going to conclude in context. Remember, when you're concluding in context, you want to refer back to HA and say HA explicitly in context. Our next test is a chi-square test for homogeneity. It's kind of hard to say. I always said it as homogeny, but that's not the same thing. And then our next one is a chi-square test for association or independence. So you'll notice that this is pretty short, and that's because between these two, there's only 2 differences, okay? So the difference is how you identify them. the name and your null hypothesis and stuff. So let's start off with the chi-square test for homogeny or homogeneity, whatever. The key question here is, do two or more populations share the same distribution for a single categorical variable? Okay, so this is very important. You have one variable of interest, all right? So how you're going to identify this is you're going to have two or more samples with only one variable. Okay, if I haven't made this more clear, it's one variable of interest. So for your hypotheses, your null is going to be there is no difference within that one variable between your two or more groups. Your alternative is there is a difference in that one variable between all your groups. The name is chi-square test, blah, blah, blah. And so now we need to dive into the other things, okay? Because everything else is pretty much the same between these two tests, okay? So now, like before, we're going to go into our assumptions and conditions, right? You got to have your random sample and selection and assignment, your 10% condition, your large counts equal to or greater than 5, and then this is a little different for your degrees of freedom. It is now the number of rows you have -1 times the number of columns you have -1, okay? This is because you have a two-way table, right? And then when you're dealing with that, that changes your degrees of freedom. And then your expected counts formula also changes. Now you can plug this into your calculator and do like matrices to get it done, or you can just use this formula. You can pick either way. There's really no like better way to do it in this case, which is your row total times your column total, all divided by your table total, okay? Your test statistic is the same as your goodness of fit. Again, don't manually calculate it, right? It's just good to know that formula in case it shows up on like a multiple choice for some reason, which is very, very unlikely because this unit is very, very unlikely to show up. But just in case, just recognize it for those multiple choice questions. And then for your conclusion, reject or fail to reject HO just like before, conclude cannot conclude HA, and then just adjust the context based on each respective test, right? So when we're talking about the context part, make sure you are going back to your null and your alternative hypothesis. So to cap the video, we're just going to talk about the other stuff for our chi-square test for association or independence. Key question here is there an association between two categorical variables? Okay, so now we have only one sample, but with multiple variables, okay? So our null here would be there is no association between our first variable in context and our second variable in context between in our one sample. And then our alternative is we're just changing one word here, association between these variables. And the name is just chi-square test for association, and everything else, guess what, is the exact same thing. So that does for everything you need to know for Unit 8 of AP Stats. Everyone, so we are on to the last unit of AP Statistics, which has to deal with inference for slope. So if you couldn't tell, it's very similar to the last couple of units, except now it's for slope, right? So got your confidence interval, significance test, and just a couple more nuances in between. So we got a new symbol here. We got this B-looking symbol, that is beta. That's the slope of the least squares regression line. So instead of trying to estimate the true population proportion or true population mean, now it's the true population slope. And we're going to do this using sample data, just like before, okay? So the big question we're trying to answer is there a linear relationship? So how the general data process collection goes, you can also do this with the experiments, but the most common way is just a random sample. So you just obtain your random sample of data points that will be plotted for you. And you need to differentiate between your explanatory variable or your independent variable, and then the dependent variable or your response variable. So this makes more sense with something like an example. So if I'm trying to say is, let's say we have study time on the x-axis and test scores on the y-axis. So if I increase study time, in my mind, I think that results in a higher test score, right? So this would be upward sloping like that. So that's what I think is going to happen, okay? We don't know if it's true. And so what I would do is if I have a student population of 500 people, then I would take 10 of those students just to satisfy the 10% condition, because we also want independence, as we'll see later. Then just measure each student's test score and their study time, right? And then we would plot those data points. So if I erase this, and we would, let's see, blue, and we'd plot those points on there. And let's say that in this case, I don't know, this is not 10 points, but in this case, there does, because we got those data points, if we draw a least squares regression line, looks something like that, that's totally off, but whatever. That looks relatively linear, and then we can estimate the slope of that and say it's like a strong positive linear slope or whatever, and so in that case, you would satisfy it. But more specifically, you can't just, randomly throw out numbers like that and estimate the points. You need to actually do a detailed procedure using a p-value or confidence interval. So let's dive into it. Confidence interval, panic, c squared, same thing as before. P, your parameter of interest, this case is beta, the true slope of the population least squares regression line, and then just talk about your two variables in context that you're trying to see if there's a linear relationship between those two. Now for the assumptions conditions, this is why you usually won't be asked to do a full procedure on the AP exam, because there's 5 of them to check. You need to check the residual plot or scatter plot to see if the data is approximately linear. Check for independence, 10% condition, or if it's independent observations, if it's an experiment. Then you got your dot plot or box plot of residuals. You don't want any strong skewness or outliers. And along with that goes, you want equal standard deviation or variance if the residual plot does not show increasing or decreasing variance. So here is what we want to see, right? So we have sample data, whatever, looks relatively linear. And then the residuals, you can see no clear patterns increasing or decreasing. But if we have data that is not linear whatsoever, you can see this is a W-looking shape. Well, our residuals is going to reflect that, right? Our residuals isn't random. There is a decreasing, then increasing pattern, right? That's not what we want. In this case right here, we wouldn't be able to do our confidence interval or significance test. The last condition is just you need random samples or assignment if it's an experiment. Let's move on to the name of the test. Just t-interval for slope of a population least squares regression line at blank % confidence. Usually that confidence is given to you. Then to calculate the interval, the actual interval, you can use your calculator or just manually calculate it. That is the estimated slope from your sample B plus or minus your critical t star value times that standard error. That formula usually is given to you directly in the problem, but you can also calculate with the formula on your reference table. That will be equal to your interval, and just keep a note degrees of freedom n-2 in case you do use your calculator to calculate that interval. Then finally your conclusion, same thing as before, we are blank % confidence interval from blah blah blah, captures the true slope, captures the slope of the true least squares regression line relating your two variables in context. So I always remember to do it in context, because AP graders love to see that. All right, let's move on to the last thing in AP statistics. It's a significance test for slopes, and we're going to be using phantoms, just like before, okay? Your parameters and your assumptions and conditions is the exact same as your confidence interval. So if you need to refresh on that, just go back in the video. Your hypotheses now, because you are doing a significance test, right? So your null is usually set to 0, because you're under the assumption that there is no linear relationship in the beginning. But this can change, like, let's say, for example, a scientist is trying to disprove a model that already shows a linear relationship, then your beta value would be, say, equal to like 1. The alternatives would be greater than 0, less than 0, or if it's a two-sided test, not equal to 0. The name of this is two-test for the population slope for the least squares regression line. And then for your test statistic, it is your estimated slope from the sample minus your population slope. So keep in mind this beta value is based on your null value. Because remember, just like before when we're conducting significance tests, what we're doing is we're running tests under the assumption that the null is right. And then based on that, we get a p-value, like how likely is that if the null was true, we'd get a result as significant or more significant as this, and that's denoted as a p-value. And then based on that, we can reject HO and then conclude HA or whatever. So to actually obtain the p-value, it's kind of interesting for slopes. You actually need the raw data if you want to use a calculator command, which is t-test for slope, but you should probably know how to manually calculate it, which is get your t-value from above using the equation, find your degrees of freedom, which is sample size minus 2, and then just use TCDF. And if you want a note about how to identify whether to put your t-value as the lower or the upper bound, pause video and get this in. All right, for the conclusion, since the p-value of blank is less than or greater than our alpha value of blank, Usually that's given as well, or if it's not given, just assume it's 0.05. We can reject or fail to reject HO and conclude or cannot conclude HA that a linear relationship exists in the population between your two variables. Guess what? In context. That's right. Always stay everything in context. Okay, and that's it. That is the entirety of AP Statistics. So go crush that AP exam and subscribe for good luck. And thank you guys for watching the video, and I'll see you guys in the next one.